Welcome everyone to the second distributed C++ meetup. Tonight we have London. Hi London, can you see me? Can you raise your hand? Yeah, perfect. And we have Stockholm. Hey Stockholm. So maybe you cannot see Stockholm, but there are people in this room. And finally we have a new attendee tonight, Berlin. So hello Berlin. Can you hear me? Yeah? Okay, perfect. So that's the first time that we have 3 participants for this event. So let's see how it goes. Hopefully it will be a nice evening. Tonight we have 2 sponsors. The first one is JetBrain. So if you go on Twitter and send hashtag SwedenCpp and hashtag CLion in one tweet and speak a bit about the event, you may receive a CLion license, which is a nice C++ ID. And JetBrain give 1 license for free. The second sponsor is King, as you might guess. You can learn a bit more about it on these 2 websites. Today we have 4 speakers representing their country. First, we have 2 of them in Sweden because we are better. We have Harald, who is going to speak about spaceship. Arvid, who is going to speak about flags. Then we will move to Berlin, and we will have Richard, who will speak about boost compute. And finally, we will be in London with Dominic to speak about trees. Tonight we have speakers, but that may not always be the case. We, the C++ meetup groups, always need to have people willing to go on stage and speak about C++ or something related to C++. So if you have any idea, please contact us, the organizer, and we will find you a time slot where you can share your ideas. You don't have to be a C++ guru to do such a kind of talk. You can do a beginner talk or something about C++ that annoy you every day. Anything is welcome. If you have questions tonight, there are 3 ways to do it. The first one is to shout very loudly and hope that someone will hear you on the other side. I don't recommend this way. No one is going to hear you, I think. So a better way is to take a mic. We will pass inside the crowd and give mic to people who want to ask questions. If you are very shy, you can go on Slido, the website, and enter the code D830, and you can ask question there online. So remember Slido D830. If I have time, we will use these questions as well. Don't be afraid to ask questions. We are not going to write down everything you say. The goal of these meetups is to share knowledge. So yes, if you have any question, don't be shy. Don't keep it for yourself. You can ask any kind of question about C++, about the speaker himself, or even question like, do we have polar bears in Sweden? I guess we can answer that kind of questions. And that's it for me. Let's start with Harald, who is going to speak about spaceships.
Thanks, Arvid, for the help. This is for the video check, but I think we have everything online. Little self-plug. SwedenCpp has finally a custom URL on YouTube, so we are easy to find. youtube.com/c SwedenCpp. Sorry for the self-plug. Distributed Meetup 2. Guten Abend, Berlin. Good evening, London. Good quell, Stockholm. SwedenCpp meeting Stockholm. This is now 11. So we have been pretty busy the last time. Less is more, let's build a spaceship. My name is Harald Achitz. I'm a senior software developer at Göttingen, or Jettingen, as we say in some parts of the country. And we use C++ to save lives. We make medical devices. You can find me online. Not that hard. About this talk, it has some history. It was originally a short lightning talk, just about how to implement comparison operators. And then last year we have a standard proposal to get a spaceship operator into C++, a 3-way comparison as other languages have it. So I merged this together and created the title. So now we have a talk about how today comparison works, a little bit what is the theory behind this, and what the future very possibly will provide for us. And the real motivator is actually this sentence from the standard proposal, which is, the goal is to be simple enough to be teachable while still enabling the most powerful and precise comparison in any major programming language. And this sounds so wonderful, right? I mean, most powerful, precise comparison in any major programming language. We want to have this. Simple enough to be teachable, simple enough, right? We buy it, but simple enough, what does it mean? So I thought I'd give this a unit test and see how simple it is to teach. Yeah, comparison and ordering. So why actually do we do this? Some things look nicer when they are in order. For example, books on a bookshelf. But mainly search works better, right? If something is in order, we can chunk it into parts. If the element is there, we have it. If not, we compare. Shall we go on this side or this side? So and always chunk in 2 parts. This is why on the very left is 2. In the exponent, we have how often we do this to have the worst case, where we either find it on the last position or we don't find it. And this scales very good, as we can see. And this is so-called O log n. And this is what people want to have. So what is required to have actually ordering? We need equality and inequality. And equality, we have different types of equality. So we have structural equality and equivalence, which means they are not unequal. So we interpreted that they are the same. Not important for our talk is physically identical. We can compare pointer. This is actually the total same object, but it's not important for us. So equality and equivalence. The difference is if I have equality and I put the thing into a function, if they're equal, they always return the same result. If they are equivalent, this is not the case. So an example would be case-insensitive string comparison. I say 2 strings are the same, and I don't care about the case, but if I get a special character from the string, I will get a different character. Inequalities, we have non-strict inequalities and strict inequalities. I've written down the comparison operators which we have, less equal than, but also subset. Strict inequalities is less, greater, and the proper subset, which is a subset with an element less. So and this is actually a short summary of what I said now, and this is one of the very few things you can remember. Different types of equality, different types of inequality, and they have a meaning. So comparison and ordering, establishing equality and inequality. How do we do this? We have the rational operators in our language. We have corresponding function objects, because the operators we cannot throw around, but this we can pass around function objects. And we have in STD algorithm a few things like lexical compare. We compare one thing after the other. And STD equal and include for comparing ranges, if they're equal or if one range includes another range. And then we have already a 3-way comparison for strings. The one is from STR-CMP from C. And we have also the string, which returns smaller 0 if we have less, 0 if they're equal, and bigger 0 if the other string is greater. Let's have a look at the rational operators. So these are the rational operators we use and we can implement in our language. And they are actually binary relation. And they create ordered sets, or ordered pairs of sets if we apply them. And the rational operators, they have some properties. And I've written them down. You don't need to memorize them, but it's good to have seen them one time. So symmetric, asymmetric, antisymmetric, reflexive, irreflexive should be this transitive, total, and trichotomy. Also symmetric and asymmetric relation. If A relates to B, then B relates also to A. And if the asymmetric part is if A relates to B, then B relates not to A. And it's much better for me to read if I have a notation that looks more like Swiss code, so it makes much more sense. If A equals B, then B equals A. If A less than B, then it cannot be the other side around. So this is the difference between symmetric and asymmetric. Antisymmetric relations. No pair of distinct elements relates to another. It makes also more sense if we have for me to read if we have concrete example. If A less or equal B and B less than equal A, then they are the same. And if it is not the case that they're not the same and one is less, then it cannot be the other, cannot be also less. So finally, reflexive and irreflexive. Reflexive, every element in X relates to itself, and irreflexive, the opposite, does not relate to itself. So it's also very easy to understand X equals X, or X is not less than X. Transitivity, if A relates to B and B relates to C, then we have a relation from A to C also. Also with code-like notation very clear to follow. A total relation, A is related to B or B is related to A or both is the case. This is also less equal, one is the case or both are the case when they're equal. And dichotomy is exactly one of them fits less, equals, or bigger. So these are properties. Why should we care about this? Well, if we implement our own operator, we shouldn't create alternative universes. We should apply this. But actually, why we care is when we have a set and we take an order relation, we get a kind of ordered set, and the properties are showed to define which set we have. And for us as developer, these are the relevant sets, or the relevant ordered sets. So we have a partial order, a strict partial order, strict weak order, and a strict total order, or just a total order. So what's the difference? So first, strict and non-strict. So the difference is which operator do we use. So for non-strict ordering, we use the less equal than operator, and for strict, we use less than operator. So this is the first difference. So partial order has, well, we could look it up. I will not read it now. The short summary is a partial order has incomparable elements. We will see in a moment what this means. A strict weak order means all elements are comparable and they are associated. Equality is equivalence. And the total order means they are sorted and the equivalence relation is equality. And it's also worth to notice that the strict weak order is a partial order and the strict total order is a weak order. And our favorite operator in C++ is the less operator because it's one sign less to type. No, it's just a bad joke. We use it a lot, the less operator, and to establish a strict weak ordering. This is for something very specific to programming languages. And strict weak ordering, we have this properties irreflexive. X cannot be less than X. They're asymmetric. If X less than B, then it cannot be the other side, and it's transitive. And then we have all elements can be compared, because if this is not the case, we have a partial order. And they can be compared if A less than B, then for all C, either A is less than C or C is less than B, or both is the case. So what does this mean? It's actually not that complex. We have here the possibilities when A is less than B. So here we have the first case, A is less than C. We have the second case where C is less than B. And we have the third case where both is the case. So A is less than C and C is less than B. And when you see it with numbers, you could say, is this not always the case, right? And no, it's not. So we have floating point values. They do not compare. And it makes also for me more sense to think about it in subsets. When we have two subsets, they can be totally have nothing in common. They cannot be compared. So why do we focus on strict weak order? Because this is what we use most. It's everywhere in the STL. We have concepts. We have a compare concept. The compare concept takes less than comparable, which is also a concept, and equivalence. So, and we have this as the function object std_less. And there, std_less is also other concepts. It's a binary predicate, which is a function object. So a binary predicate, it takes two arguments, and the predicate is it converts to a bool. And it's used everywhere. Everywhere we have sorting in the standard library, this is the relation that is available. And we can implement this relation because less is more. So this is the implementation actually. We implement just the less operator, and we can derive all other operators from the less implementation. So even we can establish equivalence. So now look at some code. How would it look in the implementation? So we can implement this as the less operator as a member function. We can implement it as a free function, taking 2 arguments. This will not compile because the function wants to access value, and value is private property of foo, so it cannot compile. So we need a friend declaration. This is a lot to write, so you will often see in reality friend pool operator, whatever. This is the reason why we have friend implementation for operators looking like this. In C++11, they can be implemented as a const expression. This works great. Also the friend inline variation, and of course the member function can be inline as const expression. And if we implement both, it will compile, but the compiler will say that this is ambiguous, and it will say it prefers the version with 2 arguments. I tend somehow to agree, but it's more to write, especially when you need friends declarations. So some less serious examples what you can do if you hate the project you're working on. I said the compiler will not warn. I've forgotten a const in the member function. These are 2 different implementations. Don't do this. You can overload this with all types. You can think about this, and in each variation. So array references and constant, non-constant, whatever, and return different results if you want. We don't even need to return a Boolean. We can return strings or whatever. This is even const expression. And I managed even to make a const expression that is verbose, so it tells you the truth. It will not just always convert to the same Boolean. So this is not what you want to implement, but if you want to overload the operator and have fun, maybe why not, right? More serious examples. This is the concrete implementation like you would probably do it. You declare the friend less operator, and you derive the other operators from this implementation. This problem is as obvious. It's always the same, and it's very verbose. Even if you implement equality, it becomes 2 functions more. And once there have been suggested a solution for this, that there is a default implementation for all these operators, but this has been hidden from the standard committee in std real ops. Anyone ever used this? No, most people didn't know that this exists. I didn't know either. If you want to use it, you're using namespace, and you have an object which has just a less operator implemented, and all other objects, all other operators for this object, they just exist. I think Alexander Stepanov proposed this, but it has been hidden in the namespace. We have other solutions today, like boost operators. Boost operators gives you much more than just compare stuff. All arithmetic operators and so on. I focus now on the comparison functions. You have to derive from these objects. There's a curiously recurring template pattern. I'm not sure if this is the best way, but it's the only way to have to do it, to tag a type, because currently we have no possibility to say if a type is a partial order, if it's a strict total order, or is a weak order type. So with this we can at least tag a type, and we know what it is when we read it. Unfortunately, we don't have mixin. I would find this much more elegant. So we need to do expert C++, right? I need to know about empty base optimization. I create my object and I derive it from this object and pass myself in. This is the way it is. Doubles, when I made this around, I've noticed that doubles also compare. This is nice. They give a lexical comparison, so they compare the first element, the second, the third, and so on. This can spare a little bit of space when you write this. So this is a little bit examples for implementation, how it is today. All this code is you can use. Standard proposal P0515, three-way comparison operator. We know it is from other languages, right? If A is less than B, it returns something that is less than 0. If A is equal, then it's 0. And if A is greater, then we get something that is greater than 0. But this is not the whole truth. The whole truth is what it does. It tells us also the type of order. If it's a total, strict weak, or a partial order, this is good. Or if it's just comparable, we have object where we just implement the equality operator, not the less operator. And it generates the other operators for us, so we don't need to write them anymore. And this will be nice. And the three-way comparison operator is actually two parts. The one is the token, that the compiler notices the token. And the other thing is what is included in CMP or compare. We don't know the header name. There's a little bit of discussion. I found this. We could also use in the standard proposal from P0768 include spaceship. I would like this most, but I don't think that this will make it. The implementation of the spaceship operator will look like this. The comparison category is returned from the spaceship operator. You take the other object. And the comparison category is one of these strong ordering, weak ordering, partial ordering. We heard about this before. And strong equality is equal and weak equality equivalent. So these objects are defined in the compare header. This object can have values. The values are named, equal, equivalent, non-equal, non-equivalent, less, greater, and unordered. And together, they give us the information about the object. So in future, we will know exactly what is implemented on the object. There will be no surprises. And we cannot compare everything because not every combination of those makes sense. So this is actually what we can implement. Strong ordering can less, equal, or greater. Weak ordering less, equal, or equivalent, or greater. A partial order is less, equivalent, greater, or unordered. Strong equality, equal, non-equal. Weak equality has just equivalent and non-equivalent. And this is the graphic representation. I hope it's big enough. This is from the standard. This comparison category, they convert down. So you can, strong ordering can become a weak ordering can become a partial ordering. If you return something from your members, if you want to go the other side, you need to implement this. This would look something like this. I have an element with a floating point value, but I want to have a weak ordering. I compare it. If the comparison of the floating point tells me this is unordered, I need to handle it somehow. Maybe I define, okay, which is the non-comparable element. I put it to the end to delete it and so. Otherwise, I return my ordering category with the proper value. We can also have a default implementation, and we need to write nothing. So this will be a total order, because integers give us a total order and we don't need to do anything. And we have all the information on the object where we had to type until now very much code lines repetitive. Yes, and that's it for me. 20 minutes, great. More information in the standard proposals. 0515, it's from Herb Sutter, and from Walter E. Brown, it's about the library support that's required. I will take questions after the next talk because I will pass the microphone directly to Arvid, and thanks for listening.
All right. My name is Arvid. I'm going to talk about type-safe flags. So let's start with, this is normally how you would define your flags, I imagine, or at least traditionally before C++11. You have an enum, C++11. You specify the underlying type and then your flags. You use it like this. Say you have a variable uint8, you can OR your enums together. You can have a function that takes a uint8, you can OR them together and pass them in. If you don't want to pass a flag at all, like none set, you just pass a 0 to that function. If you have a variable, a uint8, you can test whether flag is set by ANDing it with one of your flags. There's a type safety problem. If you have lots of different kinds of flags in your program, you might want to be extra careful to make sure that you don't ever mix the wrong flags with the wrong field. Different flags with different types. So this is kind of a motivating example. I'm not sure if you can see, but this is converting one category of flags called M into another category of flags, specifically the Win32 create file flags. There's a bug here. Maybe you can all spot it, but basically you need those parentheses because everything after the first colon, it's just integers. Their flags, my flags, everything can just OR together. So this was actually a real bug that I discovered after turning my flags into proper types. So what's the solution? A popular solution is to use an enum class. So that looks like this. You insert class in your enum definition. You define all the interesting bitwise operators for your enum class. You use it like this. Instead of uint8, you say flag t. In this case, you can OR them together. You can have a function that takes a flag t. You can pass in your flags. Notice that you can't pass a 0. There's no automatic conversion from integer 0 literal to your new flag, so you have to default construct it, which fortunately, if you don't have any other overloads, you can just use the empty braces. If you have a flag and you want to test, you have a variable of flags and you want to test whether the flag is set, you would like to be able to do this, just right, and see if the flag is set, if it's true. This doesn't work, because the result of the AND operator is another flag's t. It's not bool. It's not something that's convertible to bool or an int. It doesn't work in an if expression or if condition. And there's no way to define a free function, a free operator bool, sort of conversion operator for an enum class. And that's in my mind the main drawback. The other drawback is that if you're converting an existing set of flags, the enum class will force you to introduce another scope. So you can't be API compatible. You'll have to change where your flags are defined, specifically inside the enum class scope. So I would suggest or recommend using a class to define your flags type. I'm going to go through what I'm using. I've removed all the const expr and no except because it needs to fit on the slides. So first up, you have it's a template. You have an underlying type. You have a tag type. The tag type is the thing that makes each individual flag type unique, so that you can't mix them together. It's not used for anything other than just make every flag type distinct, unique. You have all the regular constructors, assignment, move assignment, comparison. Right, it's regular type. There's no less than or greater than it because flags are just a set. You have the conversion operators. You want to be able to explicitly construct it from the underlying type. You want to explicitly be able to convert it to the underlying type. And you want an explicit bool operator. This is what makes it possible to use this is in if conditions. And then you have all the regular binary operators that you would expect. This is how you use it. First, you define your flag type. In this case, the underlying integer is uint8, and then you just say struct color tag, for instance. And instead of enum values, you create static const exprs for each flag, the 1, 2, 4. You can create a variable or your flags together. You can have a function that takes a flag. You can OR flags together and pass them in, and similarly, there's no 0 to say that you don't have any flags, so you have to use the empty braces to default construct the flag. If you have a flag variable, you can test whether a flag is set with the ampersand, and in this case, since we have the operator bool, it will just work, so it will look good. So the other aspect of flags is how do we assign values to our flags? How do we know that we don't accidentally assign say, more than one bit to some flag or the same bit twice. So if we, for instance, would just use, assign them like this, 1 to 4, it's easy when it's low numbers, but are we sure those last two ones are just represent a single bit? Normally what we do is we align them and we use hexadecimal, and then kind of, it should be 1, 2, 4, 8 shifted. Can we do better than this? We could perhaps use binary literals these days. It's quite verbose, too verbose to even fit on the slide here. Those last two are bit 17 and 18, I believe. So I propose another way of doing this. You can define a bit type. Can't do anything. It represents an integer. The only thing you can do is to create it from an integer and explicitly cast it back to an integer. We create user-defined literal operator called bit, for instance, or something else. And we add another constructor to our flag type that takes a bit, and it sets that bit. That's the static cast to get the underlying integer back. Then we can define our flags like this, 0, 1, 2, 17, 18. So we can no longer make the mistake of accidentally assigning 2 bits. Obviously, we can still assign the same bit to multiple flags, but, well, that is all I have. Thank you.
So I think we still have some time for question to our 2 speakers. So Harald, can you go on stage? Do you have any question regarding the talk that Arvid and Harald did? Anyone? Maybe someone in Berlin? No. Yeah, we got one in Stockholm.
So a question to Harald about the spaceship. What's the biggest criticism against this proposal?
Oh, sorry. I have none.
You don't, but anyone else?
I don't know the discussion about the standard meeting, but I don't think that there is. I think that they will discuss mostly naming, as I understood, but I have no ideas about the internal what they actually discussed. But I think we can expect it to be part of C++20.
Do we have any other questions somewhere in London, Berlin, Stockholm? Okay, then I think we can fly to Berlin. Oh, wait, there is one question.
Yeah, to Arvid. Have you thought of any clever hacks to automatically generate new values for the enums?
Not really. There are like maybe macro tricks, but I've tried to stay away from that.
Any other? Then let's fly to Berlin, and thanks Harald and Arvid for these talks.
So I'll be talking about, I hope everybody can hear me in the other locations. Okay, so I will be talking about boost compute, and gonna use something that I don't know, called classic image processing as an example. So make a short introduction. My name is Richard. I'm a C++ developer in Berlin. Some facts about me. Favorite C++ pattern is almost always auto. Favorite build system is CMake with Ninja. And favorite Vim plugin is FS Switch. I had to select one plugin, where usually I have like many of them. So maybe I like another one better, but that's it from my side. Okay, so what will this talk be about? So it's, I think, more like a kind of beginner's talk. It's both, I just like wanna, get you interested and try to use Boost Compute, because I think it's a very nice feature, new feature that only I think recently got into Boost. Yeah, like I created a little like composition or a little collage of code where I just threw together some modules, some code, played around with it a bit, and yeah, started to do some like what I call creative coding or playful experimentation. So it's nothing that is like well planned or well thought out. It's just like some basic algorithms, some tools that I use to get started. So that's the kind of style that I will be presenting here. Recommended dependencies. I will be using OpenCV for basic input-output. CLEV is like OpenCL, I think, something extension wrangler. It's probably if you're doing game development or OpenGL stuff, you will know GLEV, which is kind of, yeah, I had to create a bit of a fork of this project. So that's pointing to my GitHub page, because I think like the original version of CLEV didn't have all the OpenCL functions that were needed for Boost Compute. So yeah, and as usually, it's not like kind of a clean patch or anything. It's just thrown together to make it work. Yeah, you need Boost. You can download Boost Compute, I think, separately from Boost, but starting with version 1.61 is there. I use CMake. You can use whatever you want. Yeah. So getting started with CLEV. Why am I using it? So this is like just like basic building blocks, like those little. So you say you want to start doing some stuff with with Boost Compute, and you say, oh, damn it, it doesn't work, because I don't know. I always had this idea, yeah, works out of the box, don't have to do anything. So for me, I had to set up CLEV and hack it up a bit and do this like in all my little programs, and then it works. I don't know. Yeah, it's just those kind of inconvenient little initializers to work with GPU stuff, which is needed. Yeah. Actually, if you like to, I have a USB stick, and you can copy my example code later after this talk. My laptop decided to do a last-minute Windows 10 update, which broke my Wi-Fi, so I couldn't upload it. Yeah, I have a USB stick for this. Anyway, yeah, building, I add CLEV static for building under Windows. Now, the next little annoyance that is necessary when working with laptops. Also, one of those little tricks that you have to Google on Stack Overflow or whatever to get it running. So I have this laptop which has like Intel graphics and AMD graphics. So trying to do some nice GPU computing, start up the Boost Compute library. Oh, damn it, it uses my Intel graphics cards. So I need to add this, yeah, kind of like little workaround to actually activate the AMD graphic card, the same on NVIDIA. So yeah, if you want to get started, you will probably encounter this depending on what kind of laptop you had. I think it's at least for Windows. So I have a little reading list. This is, I don't know, you can see it here. One of my favorite books. I definitely recommend it. I can show you, hopefully, yeah, on my little webcam camera demo. So nice book. All the algorithms that I've implemented are kind of from this book. It's like of an old book. So yeah, it's not very complicated, just some simple stuff. Okay. Okay, so the algorithms that I will be showing, as in this book, color distance. Like the demo that I've prepared is for pulling like a green screen from an image or from a video. Yeah, so color distance will be the algorithm to define the green screen. Pulling a matte is kind of, I don't know, filmmaker speak for creating an alpha channel. And then, yeah, matte scaling is kind of defining the limits from this alpha channel. You will see later. Blending is putting one image over another, and despilling is like a little trick, which I will show later. It's if you have a green screen and you try to make it nice, you will notice that at the fringes of your image you have a light green halo. Despilling is kind of the process of removing this little halo, which there are also some simple, surprisingly simple algorithms which sometimes do not work. Okay, simple steps how to work with Boost Compute. Init device, create a context, create a curve, build a kernel, set the arguments for the kernel, run the kernel, done. I'll show you the code in a minute. So I use OpenCV for there is a nice Boost Compute module to integrate with OpenCV, which is nice for reading, writing image, getting website, webcam support, some GUI helpers. So it's like just, I don't know. That's kind of part of the little composition or the little collage where I throw together some libraries and do something which I think is fun. Okay, OpenCL, if you know, CLCC is a CL compiler. It's useful because it will give you nice error messages for your OpenCL code, because usually you notice it most of the times too late that it's not working. Okay, we're going to the demo. So, already started my little tool. Okay, I hope, I don't know, is the font size too small? I think I can increase it a bit more. Not sure about it. Oh. Okay. So, thrown together in like one evening, mostly, maybe two. As I already told, include some headers from Boost Compute, whatever. Get up with this. See, I still need to increase it, I think. I cannot read anything. Better this way. Okay, like some of the housekeeping, create device. This is just like, I use auto like it. Okay, that's kind of the actual algorithms code, which we will get to with the demo. I will start with the demo, then it's easier to read the code, I think. Okay, no, where is my demo? Here is this. Okay, so it's a little bit tricky to get it right when using a camera in unknown light kind of environment. So I added like a template image to demonstrate the code, because the fine tuning will take, I don't know, will waste lots of time. Okay, here everything should be set up already. I have this color distance algorithm. Let's scroll to this. Kind of like, you see the implementation here. So let's start from this. This is kind of the Boost, not the Boost, OpenCL kernel. You define it like it is code, but it is actually just a string. Will be compiled later. Some simple parameters, input, output, background. This is the color distance. So the color distance is, so imagine RGB space in 3 dimensions. You have 1 point, which is 1 pixel, which is like the color that you want to match, the green screen probably, and you will calculate the 3-dimensional distance. Okay, so pretty easy to do. I don't know, you see this is kind of the code, so let's see what it does. I activated this, and I have a kind of preview which shows me results. That is, I just plot all my, this is my preview functionality. Just plot all distance value to RGB and already see, okay, it's black here, white here. So we're doing pretty good. I optimized it for this image, so that's why it's looking pretty good. Anyway, so next step would be limiting the mat to some values to make it like a bit sharper. So yeah, also like all this. So I think that's like one of the nice things with working with OpenCL and doing some image processing, like late night image processing with OpenCL. Algorithms are pretty simple. So this is like, yeah, every value is a pixel. Here I have float for RGB. Values are between 0 and 1. So set a lower limit, set the upper limit, and get a nice, clean mat. It should also do something for the live video image, but yeah, I don't see anything because it's pretty fine-tuned to this image. Okay, get back to my original image. Okay, now I'm gonna like start with the blend, which should also already look pretty nice. Okay, I have this star field background. If I go back to like this starting point which I had with the upper and lower limit like this, and if I blend, I get some kind of, where is it? Yeah, some kind of like nice. I don't know if you see it on this screen, gets a bit of transparent in the hair anyway. So let's preview this again, fix it. And where am I here? Okay, and now you see I have this like screen. You see this little green fringes? So that's where the despill come in. So let's disable this stuff again. Okay, I activate the despill and kind of gone. I can like disable the blend and you will see despill on, despill off. What does it do? Here is the kind of despill algorithm. So it looks if the green channel is larger than the red channel and then limits green to red. So for this, like the thing works pretty well for this image, will not work for a different kind of image with maybe a blue screen or maybe different brightness levels. So this book has like a whole selection of different little twists that you can do in the despilling to make it work. So it's kind of a bit, yeah. Every image needs a different kind of despill, and you can implement all this stuff in your little demo programs. Okay, I move on to some of the, housekeeping. I use this OpenCV feature named window to display this stuff, create these kind of track bars with different values to create this user interface. And how are we doing with the time? Anybody watching this? Huh? 6 more minutes. Okay, great. So I think I'm, Pardon? 16? Okay, great. What else do we have? Yeah, I'm using this, create a little user interface with create track bars and stuff. Use this like capture from OpenCV to get an image, and have all these little switches to switch between my like example image, my blend image, and let's see what else can we show. So I'm gonna like tell a bit about the background about how I came working with this stuff. I used to kind of work on a project which is like, I don't know, 10 years ago. Was called Frior, which was like C video filter API, which was used mostly by kind of VJ style applications, and always wanted to like extend it to use I don't know, like OpenGL GPU computing, but this never really worked so well. Then somebody, I think, like I got some people who saw my work on Fryer and asked me to port it to CUDA, like the NVIDIA API for running on Amazon Web Services. So that's when I first started, to actually get started with developing image processing code in GPU computing. Was quite fun, and it was also the requirement. That's why I'm not using OpenGL, or that's why I think it's also interesting to use like this kind of offline processing, which doesn't need a front end like CUDA or like this OpenCL with compute, because you don't really need it if you want to do like video processing on Amazon. You want to use CUDA. Anyway, I later moved on, which was also an interesting project where I used this kind of development. I worked for a project that did industrial inkjet printing, which had like high resolution, very large printers. And I could use I thought, hey, why not use some OpenCL for the image processing part? So I implemented actually printer drivers in this kind of style, which is also, unfortunately, I'm not working there anymore. I had already planned to do some like font rendering also on the GPU, which is also, I think, happening. I found some nice demos. I was really interested in this, but never got around to implement it. But yeah, I'm looking forward maybe that if I have some time that I will implement my printer driver in Boost Compute or in OpenCL. So that's like just for the background about how I came into doing this. Apart from this here, I don't use any kind of OpenGL integration, but there's also an interoperability module for Boost Compute to do OpenGL stuff. I set it up in one demo program, but the code is totally messy spaghetti code. I wouldn't want to show it today. You can look at it on my laptop if you like to, but it's, I thought, I'm gonna keep this example simple and just use this OpenCV integration to show the video frame. Anyways, how are we doing with the time? Okay. Apart from that, I'm gonna, I don't know, it's not like this in-depth technical talk. It's really like more to get you started. So, but I will be prepared for any like questions if you like. So what's this? Yeah, and you will find me on Twitter with this kind of handle. So great. Any kind of questions or ideas or suggestions or anything? Yeah.
We have some benchmarks to see how much using instead of raw OpenCL.
Oh, I don't have any benchmarks usually. I have to repeat the question, of course. You're asking if I have any benchmarks to see if, as I understand it correctly, if Boost Compute does introduce any kind of latency or kind of performance penalty when compared to using just raw OpenCL. So I didn't measure it, to be honest. I use Boost Compute because it's, I think, a slight bit easier to use. The API is more friendly, and I do feel I get the complete performance benefits from OpenCL. Kind of like it's mostly like a wrapper, and I think the heavy lifting happens on the GPU, from my opinion. I didn't benchmark in specific the overhead between using Boost Compute versus OpenCL, because from my perspective, yeah, I usually have lots of things to do and my time is limited. So that's why I didn't benchmark it. I don't think it makes much of a difference, and I never had a kind of problem where I felt, okay, I need to fine tune this implementation. So I never had the need, so I didn't do it. So I cannot comment on it, but I think it's, if there would be a like a vast difference, I would consider it a bug in Boost Compute. From my opinion, it's just a very simple wrapper to make the API more user-friendly. Okay, any other questions? Did you have a question, or did you just give me some sign to, I don't know what? Huh? Okay, great. Okay, then that's it for me. Hope you liked it.
So I don't know who is supposed to speak, but I think we're gonna fly to London now, and Phil Nash or someone will take over.
Okay, I think we are ready. So, hello from London. Hello to Stockholm and Berlin, came before us. Thank you for heading over. So this is C++ London. We have a usual set of sponsors, joined of course this time by our special sponsor, King, who are not only hosting this event and handling all of the AV, but also providing pizza and drinks here afterwards for the London crowd. So thanks to King for that. Now, do normally do a little bit of news at the start. Just want to very briefly remind the people here in London that we're always looking for speakers for upcoming events, and we now have a Google form for capturing that. If you just go to cpplondon.org/speak, and you can register your interest there. And then, as usual, I just list the upcoming events we've got in the calendar. ACCU conference in a couple of weeks, followed immediately by the Euro LLVM Developers Conference. And then in May, we've got C++ now in Aspen. A little bit more on that in a moment. But for me, the big news today is that we at JetBrains released Sea Lion, the latest version, as well as a new version of app code should be out as well. So check that out afterwards if you want to know more. And as always, we do the JetBrains raffle. I'll make it very brief. What I'm going to do, as I've done the last couple of times, is to throw these paper aeroplanes made out of JetBrains leaflets into the audience, and whoever grabs it wins a free license. So here goes for the first one. And excellent, I think Tristan's the winner there. He can always hand it on to someone else if he's already got one. So here's the second one. Okay, congratulations to our winners. Speak to me afterwards to sort that out. And what I'm going to do now, any complaints about the paper aeroplanes can be directed to Tristan, in fact, for some reason. Right, I've embedded Dominic's slides into my presentation here, so I'm just going to hand you right over to him now.
So this takes up from the last time we were here. I talked a little bit about some slightly bonkers proposal for C++, and this is the reason why I proposed it. So this talk is exclusively compile time stuff because runtime is totally passé now, and so we don't care about it. It's quite involved. It's a bit heavy for this evening, but anyway, we'll see what we can get through. Anyway, so it's a little bit on compile time. It's a little bit on differentiation, but it's mostly on playing around with trees and see what we can do with it. The kind of caveat with all of this is work that I did about a year ago. So if you ask me any difficult questions, I'll just evade them. Right. So the whole point of this is if I write a piece of code, I want to differentiate this piece of code without any losses whatsoever. So without any runtime losses incurred. And this is critical. So for example, so on the left-hand side is kind of what I might write, so the kind of little function. and on the right-hand side is, if I was to code it up myself, that would be the derivative. So somehow I want to get the compiler to generate what's on the right-hand side from just providing what's on the left-hand side. Now, you don't need to kind of stare at the details too much, not that important. There's just a few kind of broad brush details to convey. So the first detail about this is that the derivative, which is this kind of extra block at the end, it's in the reverse order to the original code statements. And that's quite hard to do. It's quite hard to get an out of order set of statements at compile time. So it's easy to do in order transformations. To do out of order transformations is exceedingly difficult. That's what we're going to try and do. The second observation is that the transformation there's parity between the two. So for example, in the left-hand side code, there's no if statements or heap allocations or any of that. Likewise, there isn't in the right-hand side. And this is in all the libraries that exist that do automatic differentiation, the right-hand side, so to speak, will introduce functionality that has no parity in the original code. It would introduce heap allocations, if conditions, and it ends up being horrendously slow. The reason why I do that is because it's a difficult problem to solve. Anyway, so that's what we're trying to do. On the left-hand side, get the right-hand side. So kind of some broad brush observations. So it's a pure functional algorithm differentiator, simple as that. The particular flavor of differentiation here is the adjoint. So if anyone kind of knows the lingo, that's what we're dealing with. This is the difficult type. So the required extra code is the reversed sequence of the original, and the data flow is reversed as well. And this is what is difficult to do by compile time methodology. One thing that you might think straight away is, well, okay, if the derivative statements are the exact reverse order of the original, then surely you've got a constructor-destructor pairing. You've got the initial statement and it's paired up with the derivative statement right at the end. So, for example, you got, is this? Oh, sorry, that didn't work. So, for example, statement 1, its derivative is right at the end, 1 prime. Statement 3 is kind of statement 3 down here. So that looks like you could do constructor-destructor pairing, and you can. It didn't work very well. Right, so 2 major hurdles with this approach, and these are kind of the 2 core things I tried to solve. So the first thing is you can create a tree from the expressions, standard expression tree generation. The first issue is, how do you deal with duplicate subtrees efficiently? And this is an extremely vexing problem. So you could say, well, I'll capture by reference and I'll evaluate eagerly. That'll be my solution, a standard solution. But this won't do because, just flick back one last time. The characteristics are that I've got eager and lazy evaluation. The first part is eager and the second part is lazy in the exact reverse order of the original. So pure eager evaluation won't cut. The second is capture by reference won't work either, for a reason I'll get into in a second. The capture by reference. Well, what if my tree descends into a nested function? And that this is kind of, it's very contrived, all the code examples, but just bear with it. Let's say if I swap out the multiplication of a times b, instead it calls a function called mul, and rather ridiculously, this function has a constant of 1 multiplying it. Now, if my tree traces through this and captures by reference all the terms, obviously the CM will go out of scope when I come to evaluate the tree later on. So capture by reference won't do. This is how it'd look if you were to kind of code the whole thing out. If I was to expand the nested function, okay, I need the CM up here for the original, for the plain old calculation, but I also need it later on, right at the end. So if nested variables go out of scope, I have a serious problem. Sorry. So the state of affairs broadly is eager evaluation avoids duplicate branch evaluation, but lazy is also needed, so there's a problem there. Capture by reference keeps the tree small, the object size of the tree. I can't work with references. Capture by value is too inefficient and make the tree too big, like the object size too big. So that's no good either. I need a monolithic tree, so a single tree that sees the whole call depth. It needs to support lazy and eager evaluation. It needs to be of minimal size because the heavier the tree is, the slower it's going to copy across and whatnot. And it needs to be impartial to scoping. So this kind of rules out just about every methodology under the sun. So I thought of my own. So the thing is with trees, really the only state that you need in a tree is its terminals that run, the kind of object data. Everything else is compile time, type information. The question is, can I remove all the like references to child nodes, and can I just have a representation of a tree that is purely any constants in the tree and any input variables? That's my only data, and the rest is pure type information. Well, I can. That's what I do. So the first issue on this capture-only terminals is fine, but how do I know if I've got a terminal already captured? I told you it's a bit of a heavy talk, but anyway. So how do you distinguish between one value and another value of the same type? Well, at runtime, you can just say, well, is this constant different from that one? At compile time, you can't. The only distinguishing at compile time is based on types, but constants in a tree don't have different types, so there's a problem. So somehow I need to make every unique terminal on the tree. I need to make every terminal unique on the tree, even for constants. So back to it's the same example all the way through. So if you know the first example, it's the same thing. So in this case, C0 and C1 are the same type but different values. So from a compile time point of view, if I just work on types, I'll get it'll computationally do the wrong thing. So I have to try and make C0 and C1 different types because they are different values. So, so I invent this kind of UQ function. So it's a preprocessor function. Oh, sorry. Right, so this is a quite interesting detail. This came up from the last time I gave a talk here. So last time I gave a talk, can't remember his name, put his hand up straight away and I thought I was busted. It turns out I wasn't. Anyway, so on the left-hand side, this is how I do it. I use counter, and with counter I can kind of assign different types to variables. Now, on the right-hand side, there's almost a better solution to this. So it turns out that at compile time, you can query, sort of, the address of a variable. It's not obvious that you can do that. And you kind of can do it. You can't actually do it, in fact. So you can compare whether two variables are the same. You can't actually determine what the value of those addresses are, so to speak. So the bit commented out, I can't actually compile, but the bit that's not commented out, this is actually valid C++ code. So there's almost a solution in the language already to obtaining unique types for variables, almost, but not quite, which is a pain. Anyway. Right, so with these kind of bits and pieces, we can start dealing with the tree. We've got a basic idea of what we want to do. This is the difficult bit now to talk, I'm afraid. So, to make a tree, you need certain ingredients. You need to know what the nodes are, you need to know what any constants are, you need to know what any inputs are. The data is the constants and the arguments, that's the data in memory. The rest, this is types. So the tree has a certain degree of structure to it, and this needs to be leveraged or else. So the tree has, at least it has depth. I can, of all the things I can do with the tree, I at least can query what depth I'm at. So I must make use of this structure. So what I'm going to do is I'm going to group all the level 0 nodes together, i.e. all the terminals. I'm going to group all the level 1s together, which is multiplication, and that's it. And then level 3s, which is addition, and level 4, which is the division. So at the root node, right at the top, what am I going to do? If I'm at the top node, inside of it, what does it actually do? Well, the first thing it does is see, well, is my left branch and my right branch the same depth? And if it isn't, make them the same depth. So kind of keep your compile time hat on all the time. Everything I say is compile time. There's nothing done at runtime. It is only the actual calculation. Everything that I go through here is all compile time operations. So I examine my left and right subtrees. I say, are they the same depth? If not, make them the same depth. Just pad them with null levels. Next step is to say, well, okay, merge these two, the left and right branches together. So I'd have AB and AB from the red is from the right and the black is from the left. Merge them together. Okay, now, given that all my types are unique, because I made them unique with that kind of special stuff earlier, now I can prune any duplicates. So I prune out A and B and binary multiplication, but the binary add, this is unique because it's dealing with C1. And the last step is to actually add yourself into it. So add in binary division right at the end. So with that, I have like a two-dimensional view of my tree. Just if you kind of look at the curly, this is a list of lists, so to speak. So at level 1, I've got A and B. At level 2, I've just got multiply of A and B. At level 3, I've got the additions, and level 4, I've got division. With the nested approach, it means I can search the depth I'm interested in. This makes my searching a lot faster. Right, so kind of a summary of that first step. We want to prune the tree eagerly. We want to prune out any duplicate branches eagerly. So far, they're just operations exclusively on types, and that's fast. So relatively low compile time overhead. It's moderately involved, so I need resize and unique merge and append and whatnot. And for this, I make quite a lot of use of Brigand, a good library. Right, so it gets more complicated though. Now I need to deal with values as well. So now I'm dealing with not just the structure of the tree, but actual values of the terminals. In this case, the constants like C0 and C1. So the first step is, so I'm at the root again. So I look at my left and look at my right. I say, well, what constants have I got on my left? Okay, I've got C0. And on my right, well, I've got C1. Now, I do this get longer and get shorter because it's an optimization, which I'll explain at the end. I've got C0 and C1. I bring them together into a set so as to filter out any duplicates. And I convert that into tuple because I'm going to save that data. And I need to then store. I need to store that as a member in the tree in that particular node. I'll have in that particular node C0 and C1 being stored as values. Right. A summary. This is really hard work. As soon as you start dealing with values, your compile time blows up essentially. So now I'm not only dealing with types, but I'm dealing with data as well. And this is significant compile time overhead. And the last thing is this point 4 about bridging the divide between types and data. So in Brigand, it doesn't care about data. There's no bridge functions, so to speak. But in fact, you need them because a library that only deals with types is, in the end, useless. Because you, in the end, perform a calculation. In the end, you actually run a program. So somehow you need to, when you've done all your type analysis, you need to select, values that you need. Anyway, I'll kind of dip into this next. So this select function, what is it doing? Well, it's saying, well, so it's down here is the example. So if I've got a tuple of data like 0, true, 2, and 3, and I want to select out the Boolean and the float, do that for me. So I've got a tuple of char, bol, int, and float in this. I want to say, and that's all got data associated with it. And I want to say, give me back the Boolean and the float. What function is going to do that for me? Well, you don't get a function in the typical library to do that for you, so I had to write my own. And it's not very easy to write a good version. And this function alone, just execution of this function once, costs me half my compile time. So it's a shame that library writers don't include such a function because it needs to be really, really good. Anyway, I'll not harp on about it too much. A little detail, though, is that standard get with types is useless for this. So this line here, I can't, so if I have a tuple, and I want to extract certain elements from it, you'd think, well, okay, use standard get with types. But in fact, you can't expand standard get with an argument whose type is not the same type as what you provide in the type expansion for get. It doesn't work. You can try it. So I didn't look into the implementation. Well, I did actually, but I didn't get to the bottom of it. It seems that so you got LL, which is of L, and SS, which is of S. Now these are not necessarily the same length. So SS is essentially bol and float, whereas LL is all these four. And I think this is the fact that they are not the same. Your ellipsis is not expanding on LL, but rather SS. I think there's a crux. Anyway, we can look at it afterwards. Now you need to put all this together. We've got a depth grouped list of types. We've got some constants, a list of constants. We've got a list of arguments. I passed over a list of arguments, but it's just like a list of constants. 3 pieces of ingredients, all separated out. And now I need to get back to doing what I started out, dealing with manipulating this tree. I need to convert everything to offsets. So I don't have a tree I can't walk a tree anymore because I'm basically throwing that away. I've got my, as I say, my nested list of types for all level 1, level 2, level 3. I've got my variables, I've got my arguments, I've got my constants. There is no tree anymore. Tree is useless at this stage. Somehow I need to rebuild the algorithm that I specifically want. They're all the pieces. Now what to do with it? This is the power of this method, but also the tedium of this method. I now can do anything I like. I can do any transformation. I can walk the tree in any direction. I can walk it in any order. I can optimize it however I like, because I've purged from the tree all the essence of the tree, let's say. Last little difficult bit. So, first step, I flatten my node list. So now instead of a 2D list, it's now a 1D list. And there's 6 elements. There's A, B, multiply, 2 adds, and a divide. So 6 elements. That's just a list of types. The next 2 steps are, I need my left and right indices. So if I'm at divide, at which index is my left child and at which index is my right child? I can work this out. So like binary mul the kind of the second element in, what's at its left is element 0, i.e. A. So multiply is of A and B. Well, A is at position 0. So you can see in this list here, that should be 0. And so you work your way through, like at divide, the left child is C0. Well, count back. C0 is at position 3. Likewise, the right side. So you can do a fair amount of analysis of your types. This is all. So these values are obviously type values embedded in a type. The last step is now the most difficult compile time step. So I've got a list of constants, this LC. So that refers to the binary node of add of C0 and whatever. And the other one is add of C1. So these 2 nodes, they're at position 3 and 4 in the top list. But that's no use in that state. I need to do something to this IC list to make it usable. And the operation I need to do to it is to find its dual. A dual is quite an important operation in graphs. And it's a darn difficult algorithm to implement. So this is obviously a compile time algorithm. So how do you go from 3, 4 to 2, 2, 2, 2, 0, 1, 2? Well, 3, you can just count along the positions. 0, 1, 2, 3, so that's 0. 4, I count along to 4, and that's 1. And you know the whole size must be 6. So now with these 3 indices, 1, 2, 3, my type list, my values, I'm ready to actually do something useful. This is a far cry from probably any tree analysis you might have seen. But it's all to solve those 2 initial hurdles I mentioned. So within my result operator, my assignment to the result, I can now do the calculation. So I initialize my state at the top, v equals 0, just set all the values to 0. I fill in the input arguments, so I've got 2 of them, A and B, so that'll go into 0 and 1 offsets. And now I can simply step through the list of nodes, their type list, provide it with my indices, provide it with my data, my constants, and my array of 6 values, and I can perform the calculation. I can perform the what's called the first statements that I do, and then the result I just peel it off from the last value in the array. To do the reverse order is actually trivial at this stage. For the derivative, I start here, I reverse this, I extract my results, I'm done. For those that don't know the adjoint derivatives doesn't matter, but suffice to say, at this stage, doing the adjoint derivative is utterly a trivial task. Right, some interesting results. So 2 cases. I'm not showing the code for it, it's not very important. So case 1 is, say, well, it's a tree which has 82 nodes. It's quite a fairly substantial block of code. Its depth is 37 levels, so pretty deep. 2 inputs and 12 constants. So the 2 versions that I present, one is with alt tuple, which I haven't defined, and one is with standard tuple. And this is a big deal. Which version of tuple that you use is, you'll see in case 2, is a bit of a pain point. Anyway, long and the short is, for this sort of problem, kind of 2 seconds, I can compile it. And the column in the middle, what we're interested in, the actual runtime, is fast. It's actually faster than if you were to hand code it yourself. So this approach will optimize your code better than the compiler will natively. And there's good reason why this is the case. That's a pretty good result. The second case is not such a good result, but there's good reasons why. So with the alt tuple, this mysterious tuple, so it compiles, is again much bigger tree, so it's 300 nodes, is a big function, about 300 lines worth. This will compile in a minute, and the runtime with the approach is about 5.7 compared to if you do it manually, so it's like almost factor 3. Anyway, it's not bad as things go. If I was to use standard tuple, my compilation time goes from 1 minute up to 27 minutes, which is not very good. Now, why this is a bit of a mystery. I have my own speculations, but for those who want to get into compile time programming, probably don't use standard tuple, write something else. I spent a year writing this, and so the compile time went down from about 3 hours, and it dropped down to about an hour, then dropped down to half an hour. This case, half an hour, then to 6 minutes, and then to 1 minute. I managed to get down to 30 seconds in one case, but anyway. And this is by pretty much questioning every single line of code, and as much as to questioning the very use of standard tuple. Right, conclusion. So you can manipulate a tree however the heck you want, but be prepared to roll up your sleeves to do it. The approach works somewhere between exceptionally well and acceptably well. So it will generate better code than you can write, and the compiler can optimize. However, the language really isn't quite up to this. It's a bit clunky with assigning unique types. Inlining isn't really up to it either, so I use always inline everywhere, because the standard inlining is not very good. And obviously there's something going wrong with standard tuples, something amiss. Anyway, enough of all of that. That's what I was doing for a year. Some footnotes. So kind of done with trees and whatnot. A little bit on compile time stuff. So things that I used to do all this. So the Peter Dimov's Simple C++ metaprogramming. This is the most excellent resource. So 2 web pages, best stuff I've ever used. Then compile a time compilation for large data sets, because the smallest degree of inefficiency here will cost you severely in the end. And then if you really are going to deploy something serious, you need an optimized reverse. So you can have the best of everything, but if your reverse function is lousy, your whole compile time code will be lousy. The reverse is like the gem at the heart. And Brigand library, I was really impressed. This is the one library that I think they've thought out very well. They've really done, in my mind, a very good job. Right, some kind of afterthoughts. My hang-ups with the library, with the language day. So if you look at Boost Hannah, the author has concocted some way of being able to do user-defined literals. So for strings, it's a language extension, but suffice to say, it's possible to do it today. Well, I argue that you should be able to do it with floats or ints, or well, you can do it with ints anyway. But floats has kind of been ignored as a template type, and to me, it's high time it's actually added to the language, and a kind of first-class citizen along with characters and whatnot. The next one is kind of picking up the theme from the last talk that I gave. To me, there's a third realm of reflection, which has not been tapped into at all. It doesn't exist in language or any language I know. So today, you can reflect on types and you can reflect on addresses at runtime, and this is all very good. But to me, this is still inadequate. That it'd be very helpful to be able to reflect on location at compile time. And you almost can do it from that slide earlier that I showed. It's tantalizingly close, but it's not possible. And if it were, you could do really interesting things with trees and other things. Last slide is just my kind of parting note that if you are really interested in compile time algorithms, the kind of most quirky thing that I ever came across was like this _1 and _2. So if you start digging into libraries, you think, what on earth is all that about? It's worth learning this kind of early on because it's a somewhat bizarre feature of the language that you can do this. I won't explain it, but if you get the slides, you can kind of read through it. But this function signature pattern, which I've dubbed it, is a really powerful pattern. And anyway, I'll leave it there. So questions and whatnot. Thank you.
Do we have any questions from London? I'll bring the mic over.
We have
I was just curious.
Oh, yeah, sorry.
I was just
Go
curious,
ahead,
how do you do your compile time analysis? So how do you time how long everything is taking? How do you do your hotspot analysis to work out where you need to expend your effort to optimize things?
So it's like my approach is like the equivalent of runtime. I've never used the debugger in my life. I just use print statements. I have no time for debuggers. So likewise here, if I suspect a piece of code is hot, I will replace it with a trivial function that effectively does nothing and recompile. The important detail is to recompile with a big data set, otherwise it's too hard to resolve what's meaningful and what isn't. So for example, let's say you've written a reverse function, you need to give it a set of maybe 1,000, a tuple of 1,000 to kind of really get a meaningful idea of whether it's adequate or not. So the first thing is to give it a big data set. The second is, this sort of code is quite big. Select earlier. I don't know what's happened there. I mentioned about select was a function that was critical because it bridges the type value boundary. So I know that my implementation is naive. I know it because I've removed it, put in a dummy function and recompiled, and I know compile time's half straight away. I reckon I know why it's such a problem. It's simply because the compiler gives up on optimizing it out, and so you got loads of the object code associated with it is very bulky. The last thing is actually to look at the size of the object code. It doesn't correlate very well, but it's indicative. If the object code is quite bulky, probably you're not optimizing very well. Anyway, my approach is kind of print style, hillbilly fashion. It works.
Hey, thank you. Have you tested the impact of always inlining?
Oh yeah, of course.
What was it roughly?
It'd probably double in runtime. I mean, without using force inline, I may as well just give up. It's a complete waste of time to do this. That's how bad it is. It's the competitor implementations, which are 2 or 3 times slower. It's the difference then is negligible, and at least for large functions that we're trying to differentiate. So, for example, if case 2, it's a tree with 300 nodes, the compiler simply doesn't deal with inlining a lot of the work out, and so your runtime is nothing special. It's a major issue.
Any more questions in London? Then do we have any questions in Stockholm?
Yes, we have.
Okay, take it away.
Hi, thanks for a fascinating talk. Perhaps I misunderstood you, but I think the way I understood you, you said that the old tuple function was never implemented. So then...
No, I'm glad you brought this up. I forgot all about it. I just said I'm not explaining it right now. So in fact, all it is, this is where the kind of mystery creeps in. Alt tuple is standard tuple, just renamed. So I went into GCC implementation of standard tuple, pulled out all the pieces that I want, renamed it, put it in a different file, and that's it. So there's a mystery for you. So here's my answer to where I think things are a bit quirky. I argue that the compiler treats anything that's not in the standard namespace as second-rate code, and it doesn't really care about it. And it's a secret flag somewhere. That is, I'm afraid that's as deep as my thoughts go, but that is honestly the case. In the sense that alt tuple is standard tuple, just with what I need and nothing more.
Yeah, I think that's answered the question. Any other question?
Yeah, did anything. Oh, I've just taken the bare minimum from it of what I need.
Yes, and other question regarding your performance benchmark. I might have missed it, but did you mention what platform, compiler, and standard library implementation you were using?
No, I didn't, but it's the lamest computer you could buy. So it's like it's a Intel i3 from about 5 years ago with 4 gig of memory. And I'm using G++7. And I don't know which version of the standard library, but quite frankly, I don't use the standard library pretty much. So that's another, but it's G++7. And I'm using C++14 language.
Okay, thank you.
Anyone else in Stockholm? I think that's all for us in Stockholm. Someone in Berlin, maybe?
Any questions in Berlin?
We have a question.
Hello, thank you. Thank you for the great talk. On one of the previous meetups here, I've learned about Eric Niebler's Boost Proto for the expression trees, I think. Does this anyhow relate to the work that Niebler actually did there?
Yeah, so this is an excellent question that I feared someone might ask. So I studied Boost Proto for about 6 months. I'd never actually used it. I just read all his articles, which are quite hard to get hold of now. However, I tried to implement what Boost Proto tries to do in a kind of simplified manner. So my problem with Boost Proto is that it's object-based. So you have an expression and you provide a grammar and it transforms the expression for you. So the kind of canonical example he uses is you got two vectors, A and B, and you say in parentheses A plus B and then angle bracket, square brackets, some element. So it's a really naive thing to do, and Boost Proto will rewrite that to A square brackets like 2 plus A square bracket, B square brackets 2, something like that. That's a kind of simple case of what Boost Proto does. Now, the hang-up with Boost Proto is that you pass around objects. So you have an object of the expression, and you provide it to the transform function, and it returns another object of a different expression. I have a big problem with dealing with objects because these are big objects. A tree with 300 nodes in it is quite heavy in memory. There's the whole emphasis on trying to make this tree as light as possible. Just the constants, just the terminal values, nothing else. So the last thing on earth I want to do is create objects and transform them to different objects, because by the time I've done all that, I've thrown away all the runtime performance. The second thing is that I can't do any of the pruning eagerly. It has to be lazy. I have to build the entire original tree first, and then with that, do the full transformation. Whereas what I really want to do, because it's much more efficient, is to search for duplicate branches as I'm building the original tree in the first place, and do it with just types, because that's all I need is just types. As soon as I start dealing with objects, with data, compilation goes through the roof, compile times, the actual object compiled is poor, and it's just a disaster. So it's nice for kind of pretty little short statements, but for anything kind of serious, I don't think it would cut.
Thank you.
Was there any more in Berlin?
I think that's it from Berlin.
Thank you, Berlin, for the questions. Thank you, Stockholm, and thank you, Dominic, for the great talk. Okay, before we finish, I think we've done that slide. So I just wanted to wrap this up. And before we do that, I actually have one more thing. Now, if you came to the London meetup last time, this bit might be familiar to you. But earlier on, we looked at this slide where I introduced the upcoming events. We got ACCU, C++ now, CPPCon comes later, the meeting C++. But in February of next year, there's going to be a new conference called C++ on C, which I'm organising, which is going to be in the UK. And it's going to be a pure C++ conference, but an international conference. So this is entirely relevant to those of you in Stockholm and Berlin. And it's going to be a 2-day conference with an extra day of tutorials as well. There will be more information coming on the website later, but I just wanted to show you a couple of slides from the venue because I'm really excited about this. It's actually set in a theatre that's set in the cliffs overlooking the sea, hence the name. So it's got sea views on 3 sides, even from the bar. I've got a minimal website up at the moment. It's due to be completely overhauled soon. That's where all the information will be, but there's already a button there where you can register your interest. I do need to look into the how GDPR affects that. I haven't done that yet, but it's just a Google form at the moment. So if you're interested at all, sign up on that link, just cpponc.uk. And with that, we really have come to the end. So I want to thank everyone from all 3 locations tonight, and also King for hosting and sponsoring the event. Thanks for everyone for coming. I don't know if anyone in Stockholm or Berlin wanted to say anything as well. But if not, I think we'll probably finish.
Yes, thanks a lot, Phil, and thanks a lot for the other locations. That's it for us as well.